All right, ladies and gentlemen, we'll get ready to start today, chapter 5. And look at this behind me. It's light outside. I'm doing this in the afternoon, so let's see how this goes. But we're changing up what we're talking about, and today is conceptual in nature. There's no homework today. There will be some quiz questions, of course, with the lecture, but there's no homework today. And there's no help session today in person. There's no help session in class on Friday. We're just going to have 2 video lectures this week, and then start it again on Monday of next week, the 19th. And just to let you know, we're going to start re-looking at things again, but in a different way, because we're going to be talking about the second law of thermodynamics. And the funny thing is, nowhere in chapter 5, this is chapter 5, do we give you the second law. That's not until chapter 6. We're going to give you all of these basic ideas, conceptual ideas about the second law. We're going to formally give you a statement, a numerical statement, not numerical, equation for the second law in chapter 6. So let's just refresh our memory about the zeroth law. The zeroth law basically says a temperature difference is required for heat transfer. And the first law states that the energy cannot be created nor destroyed. Okay, and so we are going to get today to the second law, and the second law is going to basically say, in many different ways, we can say it many different ways, but the second law is going to say no process ever happens ideally. Now, as engineers, our goal is to have processes happen as close to ideal as possible. We don't want to have a lot of inefficiencies in our processes, but we have to understand that perfection is not something that we can actually attain. It's a goal that we can reach for, but it's not something we can actually attain. Now, I want to talk just a little bit about this first law. Remember, the first law is saying energy cannot be created nor destroyed. So why are there signs on light switches everywhere that says, please conserve energy by turning off the light? Or why did your parents tell you, close the refrigerator door, you're wasting energy? Why? Because in reality, energy cannot be created and it can't be destroyed. So keep the refrigerator door open. You're not destroying energy. Keep the light bulbs on. You're not destroying energy. What is actually being said here is we're trying to when they ask us to turn off the lights and to close the refrigerator door and things of that nature, we're asking us to conserve the type of energy that we have. Okay, electrical energy is very useful. Okay, we don't want to just waste it. That coal that is inside of your refrigerator, it's very useful. We just don't want to waste that. So we don't want to waste the quality of the energy. Now, don't confuse this quality with X, the quality from a liquid vapor mixture. I'm talking about the type, the level of the energy that we're dealing with. There's multiple levels of energy that we're going to be dealing with. Okay, so wasting energy is synonymous with converting something from a more useful form to a less useful form. So whenever we turn on a light bulb, there's reducing heat, and that heat's going to go out into the room, and of course it's going to be there. It's going to produce light. But trying to then harness that and put it together so you can charge your cell phone is very, very difficult. That's why we want to keep those things in the best form that we possibly can. And so we could have 1 unit of high quality energy, like electrical energy, could be worth more than 3 units of a low quality energy. Okay, so let's talk about the second law and see what that means. So intro to the second law. Okay? We know the following things. No process can violate the first law. It has to. You have to satisfy the first law for the process to be valid. Okay, that must be the case. Okay. However, satisfying the first law does not ensure that the process occurs. Okay, we've been assuming so. I've been giving you real processes, but satisfying the first law is not the end all be all. So I'll write here, satisfying Okay, so here is an example. I have a mug here. I don't have a mug to show you, but I have a mug. I'm going to pretend like this is a mug, and I'm going to say it's full of hot cocoa. Okay, this is a phone call. Let's pause and see what's going on here. It's my wife. I should answer. All right, so we're going to talk about hot cocoa here. Hot cocoa. Oh, and also my kids are awake, so they can help me out. Look at this. We have this neat mug from Mario. This is a Mario mug. Has all the different characters in Mario. There's some people we don't understand. Like, who is this dude?
I think that's some character from Dr. Mario. Same with the X dude and the V dude.
The V dude. Okay, we don't know. This is very interesting, but this is.
Same with the A dude. We don't know who the A or the Z dude is.
You don't know who the A dude or the Z dude is. All right. Well, anyway, this is our mug. Okay, mug. I'm gonna write it here. How do you spell cocoa? C-O.
I think the correct pronunciation is cacao.
Cacao. Okay, whatever. I'm the teacher here. You leave me alone. Okay. Okay. Now I have hot cocoa in this mug. I don't really have hot cocoa. Why did you bring me a mug with hot cocoa in it?
Because we do have a hot cocoa packet, but I didn't want to take the time to make it. You want to be finished with the problem.
Yeah, I would be. Okay. So when this is full of hot cocoa, all right. Now what happens? When this is full of hot cocoa, what happens is heat leaves this mug. It cools down because otherwise we're going to burn the top of our mouth, right? We're gonna burn the top of our mouth.
That's happened to me before.
It happens to everybody. Okay, so you wait, you blow. Convection, everything happening. All right, now this is saying delta U is equal to Q minus W. We're assuming that this is going to be a closed system, all right? The hot cocoa is a closed system. Whoops, why can't this select this? Select a different, well, anyway, this is a closed system. This mug is a closed system. We're assuming no mass is leaving. I'm not drinking it yet. Closed system. Delta U is equal to Q minus W. Now, let me say this. Now we have a cold mug of hot cocoa. It's cold cocoa. Is that such a thing? It's cold cocoa. We have cold cocoa. Cold cocoa.
Because if it's hot cocoa and it's cold, it's not hot.
Yeah, that's right. I mean, come on. That's right. If it's cold cocoa, it's not hot. It's cold. So we now have a mug of cold cocoa. Okay, now tell me, Lila.
Cacao.
Tell me, Lila. If I leave this on the kitchen table, will it magically heat up?
No.
Probably not.
Probably not. Let's be more definite. Let's be definitely not. Definitely not. Definitely not. It will not. You know this. My 6-year-old daughter knows this. You're going to put this out there. It's just going to cool down. It's not going to heat up. But you know what?
Well, I'm only in first grade.
I know you're in first grade, but these are college students, and they should know.
Remember when I got a 3 on one of your final third
Yeah, I know.
exams? I think I was 5.
Yeah, I know. When Jonah was 5, he took one of my exams and got a problem right because it was a fluids exam because you knew what the definition was.
Yes, it was a fluids.
Hey, these people are paying big money for me to lecture here, so I need to finish lecturing. Yeah, they're paying big money. Big money.
Yeah.
Yeah,
I know that.
Okay. All right. So now this cocoa, and we said we're not saying that heat is not magically going into the cocoa. It's not. But if we were to follow the first law, delta U is equal to Q minus W, we are not violating the first law at all. We could have heat going into that, naturally coming from the environment and going into that cold cocoa and heating it up. And that would not violate the first law of thermodynamics at all. And that's why we need a second law of thermodynamics, because we know this does not happen. This does not happen. So there's something else that we must satisfy to make sure things are okay. Okay? So we can do this many different ways. My cocoa example is one of them. We could do heating the room with a resistor. You heat up a resistor, that resistance heating heats up the room. We cannot heat up a room and put energy back into that resistor. Transferring heat will not generate energy directly, okay? So there's a direction of processes. That's the thing here. There's a direction of processes. There's a direction of processes. The first law provides no restriction on the direction of processes. The second law does, okay? You can throw a ball, throw it, and then the first law of thermodynamics would say that you could put your hand out and the ball would jump back into your hand, okay? The second law knows that that is not possible. So we're going to have a direction of processes, and I like to think of it as there are two switches that must be followed. First law switch and a second law switch. Okay, and you're going to have a process going through, and I don't know why I can't choose a different color marker, but I will just go with it here. This process here is going through, and it must have the first law switch go down, must satisfy it, and must also satisfy the second law switch. Now, every problem you've had so far, we know the first and second law switches are both satisfied. But now we're going to take that away, and we're going to ask you to verify. I want you to check those things. Okay, so that's what we're going to be doing in this chapter. That's the end of our first lecture segment, and we'll come back and talk more about the second law of thermodynamics.